Hello, everyone. This is the talk called Lazy Programmer's Guide to Writing Thousands of Tests. It's about property-based testing. If you're not a lazy programmer, maybe this talk will not be of interest to you. But like most people, I'm in fact a lazy programmer. So I don't want to write lots of code if I don't have to. And property-based testing is one way to avoid doing that. So my name is Scott Wlaschin. And where is it? There we go. Scott Wlaschin, fsharpfundandprofit.com. So the examples in this talk will be kind of F# code, but the language is not really important. It's the concepts that are important, and these concepts apply to pretty much any programming language. So here we are. The NDC community, unfortunately, is social distancing. So I'm working from home like you are. Hopefully we can all stay safe and still have some fun. Right. So in order to set this up, I'm going to tell you a story. It's a semi-made-up story. Part of it's true and part of it isn't. I kind of exaggerated. But I mean, I was working with a remote developer a long time ago in a galaxy far, far away. And for the benefit of the story, I'm just going to say that we needed a function that would add two numbers together. Okay, it was more complicated in reality, but there we go. How do you add two numbers together? And so the remote developer says, sure, I've just finished adding the add function. I'm happy. And I say, have you written unit tests? And they say, you want unit tests as well? Yeah, okay. They kind of sounded surprised. So they wrote a test. Given inputs of 1 and 3, I would expect the output is 4. That was their unit test. And then they say, okay, can we call it done? And I would say, well, actually, that's only one test. How do you know it doesn't fail for other inputs? It's just like 1 and 3. So they say, okay, let me write another unit test. And they said, okay, I just wrote another awesome unit test. They thought they were, a certain kind of developer who said that kind of thing. 2 and 2 is 4. And that's an awesome unit test. And I wasn't so impressed. I said, you're testing for special cases. How do you know it doesn't fail for other tests that you haven't thought of? And he was like, you want more tests? I've already written 2. Well, how much do you want? And that is a good question. How do you know that you have written enough tests? And this is quite a deep question. How do you know that you have enough tests? Is 2 tests enough? 5 tests? 100 tests? The whole point of testing is to gain confidence in the implementation. And you can have 100% test coverage and still have, bad implementation. And you can have, a small test coverage, but still have very high confidence in the implementation. And so that's one of the things that we're going to try and talk about. So in this case, I didn't trust this person to write unit tests. So I thought I'd write them myself. So I had a look at the existing tests. This is F# code here. When I add 1 and 3, I expect 4. And I do the add function, and I assert that the answer is 4. And that passed, okay? And then let me write another test. If a 2 and 2, and I call the add function, and I expect the answer to be 4. Okay, so that's good. That one passed the test. So let me write a test, okay? So when I add -1 and 3, let me do something tricky. I add -1 and 3, and I would expect the answer to be 2. And this test failed. So I thought, okay, well, that's kind of funny. Let me go and look at the implementation. Let's just check and see how everything is. So here's the implementation. To add two numbers together, return 4. Okay, and in F# you don't need a return keyword. So that was the entire implementation. And I was like, what is this? This is terrible. So I wrote back and I said, I'm going to write the tests and you're going to make them pass, okay? I don't trust him. And he said, sure, no worries. So let me write some more tests. I'm going to 2 and 3, I expect 5. And he wrote his implementation passed that, okay. And then if I do, let's say 1 and 41, I'd expect 42. And that test also passed. So okay, maybe his the implementation is getting better. So let me just check the implementation though, just to be sure. So this is the implementation, And if the input is 2 and 3, the answer is 5. And if the input is 1 and 41, the answer is 42. And in all other cases, the answer is 4. And, like, this is not a very good implementation. This is not a very good implementation. And I'm saying, so I said, what are you even doing? You haven't even implemented anything yet. You've just made the test pass. And he said, chill out. I'm totally following TDD best practices, which is you write only enough code to make the failing unit test pass. And that's exactly what he was doing. And, I think that's, I'm not sure that's quite what they meant when they said that. But, he's following it literally. Okay, so I thought, well, let me just try and make it more complicated. I'm going to have a whole set of test data, a whole array of test data, and for each answer in the array, I'm going to see if the actual answer matches the expected answer. And that passed. And I had a look at implementation again, and of course, you can guess what he did. Basically, every possible thing that was in the input was hard-coded. So we have a problem. Houston, we have a problem here. It dawned on me that I was dealing with a certain kind of person, the legendary burned-out, lazy, malicious programmer called the enterprise developer from hell. And you might have, in your life of developer, you've probably met people like this. They are lazy and they're also malicious, and they also are not, sometimes they just try and make life worse for everybody else. So, and I've used the evil Garfield as the symbol for this person. So I've got to rethink my approach. The enterprise developer from hell will always make specific examples pass, no matter what I do. So what can I do? I have to not use specific examples. But how can I write a test without having any examples of what I want? Okay, so let's use random numbers. So this way he can't guess what they are. So I take a random integer and another random integer, and I put down the expected answer, and I put the actual answer that I got from calling this function, and I check that the answers are equal. And this is fantastic. Let me just do it 100 times, just in case he gets lucky with the two random numbers. So I'm going to do it 100 times, just so it's not a coincidence. Okay, so there's the final test. 100 times, take two random integers, add them together, and make sure that when we call our new add function, that they get the same answer. So this is great. This is great. The enterprise developer from hell cannot possibly beat this this test. However, we have a bit of a problem because I have basically re-implemented, I'm using the built-in addition function. And if it was a brand new kind of functionality, I'd have to re-implement the functionality in the test to check whether I got the right answer. And this is a really common problem in testing, is you basically have to re-implement what you want in order to test it. And that's, that's an anti-pattern. You do not want to be re-implementing things to check that they work. So this is a problem. So how can we fix this? How can we fix the problem of implementing add without using the add function? All right. So if we can't test it by comparing it with something we already know, how can we test it? So how would you write, this is a question for everyone listening, how would you write a test for an add function without re-implementing add or without using any of the built-in libraries and without using any specific examples, like 2 + 2 = 4? So that's the challenge. And this leads us to property-based testing. So in order to implement it, we need to know what the requirements are. And what are the requirements for the add function? It's hard to know to get started with these things, but one way is to think about, if you don't know what the right answer is, you can often compare it with the wrong answer. So we don't know what add should do, but we know that addition is different from subtraction. How does addition differ from subtraction? Well, one simple thing is that the parameter order makes difference. So in addition, it doesn't matter which order the parameters are, but subtraction, it does. 5 - 2 is not the same as 2 - 5. So we could write a test for that. Okay, so that's a little difference we can write a test for. So here's our test that checks that little thing. So we say that whatever the thing is, it doesn't depend on parameter order. So we take we do what we did before. We take 100 different random numbers and we add them together. And we also add them together with the parameters reversed. Okay, and then we check that we have the same answer. And if we do have the same answer, you know, it's a quite a good test. It's not 100% perfect, but it certainly eliminates the wrong answer of subtraction. Okay, so a whole bunch of incorrect implementations have been eliminated this way. Now, of course, the enterprise developer from hell is clever and they're evil, and they will respond with this implementation. To add two numbers together, you multiply them. Now, this passes the test. He's particularly easy. He's being very, very evil today. Unfortunately, this test passes with this bad implementation. But we're getting the hang of it here. We can keep doing the same thing. So what's the difference between addition and multiplication? Well, that's a bit trickier, but you know, a simple one is if you add one and you do it twice, that's the same as adding two. But if you multiply by one twice, that's not the same as multiplying by two. So let's turn that into a test as well. We're going to call it two adding ones. Two of adding ones is the same as one add two. So here we go. So again, we'll take our random number. We'll add one and we'll add one again. And the second one is we'll add two. And they should be the same answer. Now this will eliminate the multiplication implementation. So that passes. But the enterprise developer then says, okay, I'm going to implement this with minus y, with subtraction. And this passes the test because subtracting one twice is the same as subtracting two. So when I try and do this test will now pass with subtraction as the implementation. But we have the previous test as well. So when I add two numbers, the number it doesn't depend on parameter order. So the previous test now fails. So the combination of these two tests is what narrows it down. Each individual test eliminates a set of things, and when you combine the two tests, they really start narrowing it down a lot. So can the enterprise developer from hell come up with a test that implementation that will fail? Let's see. But yes, he can. And this is his implementation. To add two numbers together, you return 0. And actually, this passes all the tests because you know, doing it twice, that passes, and it doesn't depend on the parameter order, that passes. So, okay, how can we write another kind of test that eliminates this kind of implementation? And the problem is that we're not, we haven't really understood addition, because there is somehow the addition function is the output has to be connected to the input somehow, right? And it does depend on the input, but we don't want to have, we don't always know how it depends on the input because without actually re-implementing it. But is there a trivial input that we do know the answer to, like without having to re-implement anything? Is there an input of add that we always know what the answer will be? And the answer is yes. If you add 0 to something, that's the same as doing nothing. So let's write a test for that. Okay, so we're going to take do it for 100 times to do a random integer. We're going to add 0 to it, and then we're also going to have the original number, and they should be the same. I should be untouched. So if we add this extra test to it, this actually will pretty much defeat the enterprise developer from hell. We have this test, we have this test, and we have this test. And if you combine these three tests together, any particular implementation will be much harder to, it's much harder to have a sneaky thing. In fact, this is not 100% perfect. I mean, this is pretty true. There is actually one way of making this fail, but we can extend this idea to make it so it's literally impossible to fail. So that's the idea of property-based testing. We're not testing individual examples. We're testing properties of the function, the fact that it's independent of parameter order, That's a property of the function. No matter what the inputs are, it's always true. It's a invariant of the function. Adding 0 is the same as doing nothing. That's always true, no matter what number you have as input. So without using specific examples, we've narrowed down the implementation of add. So let's refactor this out. Let's extract the shared code. We've got a lot of common code here. So what we're going to do is write a method or a function called Propertybased, and it has a parameter, which is the property function. This is what we're going to be passing in. And in this particular case, the property function takes a pair of integers as input and returns a Boolean as output. It always returns true or false. And so our generic property function looks like this. We take a random integer, we take another random integer, and we call this property function with these two integers, and the result is either true or false. Okay, and we always want the result to be true. This property should always be true. And if it is always true, then we have a good idea that the property passes. Okay, so this property function, technically it's a function. We just generally call it a property. It's like something that's always true for a set of inputs. And so this is basically property. Basically we've written our property-based testing framework right here. It's not a framework because it's a single function, but that's how simple it is. Right, so this is what the tests look like. We have a property function, which is like the commutative property where the parameter order doesn't matter. And the property function just like takes the two inputs, calls the function with the inputs reversed, and the answer should be the same. And then our actual tests look like this. We have a test for the particular thing, and we just check that that particular property function is always true for random inputs. So here's the second property. Now, we only need one of the two inputs, but here's the example. Here's written as a property. We add it once, we add it twice, and the answer should be the same. So it always returns a Boolean. These properties are always Boolean returning functions. And again, if we want to use it in a test, we take this Boolean returning function and we pass it into our property checking thing, which again, it checks that property for 100 random inputs. Okay, now if you're a mathematician, you'd recognize adding one twice is basically a very crude version of associativity. So the real addition property is associativity. And the third one, adding 0, we call this the identity property. If you add 0, it's the same as doing nothing. And we write a test using that. And there we go. So let's review what we've got. The parameter order doesn't matter. Doing add 1 twice is the same as doing it as adding 2, and adding 0, doing nothing. These properties apply to all the inputs no matter what they are. No matter how random they are, these things are always true. So we have a very high confidence. Going back to my original statement, we haven't tested all 4 billion inputs, but by choosing random inputs and they always work out, we have a high confidence that the implementation is correct. So we've basically written 3 tests, and rather than 3 example tests, we actually have 3 property tests. Now, these things have words in mathematics. We call this commutativity, associativity, and identity. And this is not just a test. This is actually now a specification. Anything that implements these 3 properties is addition. Okay, that actually defines addition. So by defining it, you literally can't, if you pass these 3 tests of these 3 properties, that meets the specification of what addition is. So you literally cannot create an incorrect implementation. So that's the idea behind property-based testing. You can see it's pretty straightforward. It's something you could write yourself in a few minutes if you wanted to. But yeah, I just want to re-emphasize that by using this kind of property specification approach, we've actually understood the requirements in a much deeper way. If we just said that 2 + 2 is 4, that's just an example of what addition is. Because 2 × 2 is also 4. It doesn't really narrow it down. It doesn't really tell you what the true meaning of the thing is. If we use specifications like this, it really helps to drive a deeper understanding of what we really, really want the system to do. Right, so why bother with this example? This kind of malicious programmer is realistic, very unrealistic, very over the top. Nobody would ever do this, surely. So here's a way of thinking about it. We have evil people, we have stupid people, and we have lazy people. And it doesn't actually matter which kind of person you're dealing with, because whether they're evil, stupid, or lazy, they will still mess up your codes. Stupid people can cause bad bugs just as much as evil people. So, it doesn't really make any difference. And there's actually one person I've always had to deal with, one particular stupid person in my career that I've dealt with a lot, which is kind of frustrating. Here's the stupid person, it's me. And when I'm writing code for the first time in a new project, I often don't understand the requirements, and I often write code that I'm not happy with, and it often has bugs because I didn't understand something properly. And so I'm the real enterprise developer from hell myself, especially myself from 6 months ago, who was too lazy or too stupid to do something. And I'm sure that a lot of you have the same experience. You look at old code and you think, yeah, I could have done this completely in a different way, because now that I'm older and I understand the system better, I could probably write it in a much better way. So that just comes from, there's nothing wrong that happens to all of us. It just comes with learning about the system better. Right. So it's not because I'm evil, but just because I'm unaware and I'm blind sometimes. So doing the thinking, and this is the lazy thing, we're too lazy to think. If I had spent more time thinking about the properties, that would probably help me get better tests. And also it helps me understand the requirements better. If I ask, well, what is a property that always has to be true? If I can't come up with a good answer, it means that I probably don't understand the system yet. All right, so that's the homemade way of doing property-based testing. But let's look at a library. You don't really want to write your own test this way. And the library is called QuickCheck, and it's a toolkit for doing property-based testing. It was originally developed for Haskell, but the ideas are now available. Pretty much every programming language has a property-based testing framework, or sometimes it's called QuickCheck framework. Very, very good. I highly recommend that you look into these. So this is how it works. You have this library has an API, and inside there's two things called a generator and a shrinker, which I will talk about. So you have your property, which remember is a function, and it's a function that returns Boolean. You pass it into this API, and the first thing is that the generator part generates random inputs to generate random inputs for your function. But then the second part, the shrinker, creates minimal failing inputs. The problem with having completely random inputs is they might be some incredibly random large number, and it doesn't really tell you what's gone wrong. It says, yeah, well, this thing failed if you pass in 475 billion or something. But yeah, that's not very helpful in understanding what's going on. So having a minimal failing input is really, really useful. So let's start off with showing you some code. So here is our correct implementation of add using the built-in library. So here's our property that should always be true no matter what the inputs are. And then in F#, which is what I'm using, you just say check this property using the built-in QuickCheck library. So that's how simple doing it is. It sounds like it's something kind of complicated, but it's actually really simple. It's just a few lines of code. And when we do this test, if everything runs well, we'll say a message like this: we passed 100 tests. So what it did is it generated 100 random inputs for this property, and every single one of them returned true. Right, so let's look at how the generator works, because it's kind of interesting. First of all, there's generators for all the primitive types. There's an int generator, there's a string generator, which is really useful because it generates random Unicode strings with non-printable characters and all sorts of weird things in it, which you might not normally think about if you're testing your strings. There's a Boolean generator, so it just generates random Booleans, true and false, whatever. So those are the kind of basic primitive generators. And then what you can do is you can generate compound types. So if you want to generate pairs of integers, you just say, I want you to generate pairs of integers, and it will do that. Each part of the pair is going to be a different integer. In functional programming, we have the optional type, and so you can generate optional types the same way. Sometimes it'll be something, and sometimes it'll be nothing. And if you have your own custom type, so I'm defining a custom type in F#, and there's 3 different choices. This is kind of like an enum, you can think of it. There's a red case, there's a green case, and a blue case. And in the green case, there's an integer associated with it, and in the blue case, there's a Boolean associated with it. So this custom type, the QuickCheck library will normally be able to handle it nicely. It will just generate random instances of this thing too. So a random green, a random red, a random blue, another random green, and so on. So in functional languages, we have something called algebraic data types, or I like to call them composable data types, because in a composable type system, bigger types are built from smaller types, just like using Lego. And because they're built from smaller types, if you can generate random data for the smaller types, you can also generate random data for the bigger types, because they're just composed from the smaller types. So it really, really fits well with property-based testing, unlike the object-oriented style of defining classes, which doesn't really fit so well. Right. So here is our property. I'm going to use this property again. And we have these 2 parameters, x and y. And when you pass it into the checker, it says it figures out these are integers. So it will generate, it automatically figure out I need to generate pairs of integers. So it generates pairs of integers, and then it passes them into the property, and it does it for 100 times, and then it sees if it's true for every time. So this is how the checker works at the crude level. Basically, again, it's something you could write quite easily. Right, now here's the nice part, which is this shrinker component for dealing with failure. I'm going to demonstrate that. I'm going to use a very crude example, which is we have a property called the number is smaller than 81. Now this property will obviously fail for numbers that are bigger than 81. So we know this property will fail, but let's see if the shrinker can help us figure out exactly what the boundaries are. If we did this property with our random one that we implemented by ourselves, it would just generate random integers, and it might fail with, like say, some very large random number, which really wouldn't be very helpful to help us narrow down what the problem is. So let's see what we can do here. So we know this is going to fail. So the QuickCheck will generate a whole bunch of random integers, and it gets up to 100. Now, all the other ones pass, and when it gets to 100, it fails. Right. Now, rather than just saying it failed with 100, we're going to start again and see if we can narrow it down. Okay. So what can we do? Well, what we do is we generate numbers smaller than 100, which is why it's called shrinking. So we generate numbers up to 100 and see how it works. So when we generate numbers up to 100, it doesn't generate all of them. It takes kind of a kind of diminishing series that get diminishing as it gets closer to the answer. So in this case, it generates 0, 50, 75, 88, 94, 97, and 99. Now, in this case, when we run those numbers through the property, it fails at 88. Okay, well, that's good. We're just going to start again. So now we're going to start shrinking from 88. And this will generate all the numbers up to 88. 44, 66, 77, 83. And 83, it fails. So let's do it again. So here's our list for 83. And we have 42, 63, 73, 81. So it fails at 81. All right, and then we do it again. So we generate all numbers up to 81. Now, if we run this, these ones all pass. So we know that all the ones up to 81 pass, but 81 fails. So it has figured out that 81 is the smallest failing input, which is great. So when we run this thing, if we ran it interactively, it actually says the answer is it's falsifiable, meaning that there are some values where the property is false. It did 23 tests, it did 3 shrinks, and the smallest failing one is 81. So it literally tells us where the boundaries are in our errors, which is really, really, really nice. And it works for more compound types. Obviously, I used integers as a simple example, but it will work for more complicated types as well. It'll try and find a smallest thing that will fail the test. Right, so that's how property testing works. And people, when they see this, they say this is great. But when they try and do something, they kind of get stuck. It's like, how do I even choose a property for my system? So, what properties should I use? I can't think of any when you actually try and do it. So I'm going to show you some properties that you can use to get some ideas from. So the first one, this is probably the most useful one in general, is that you take different paths, but you get to the same destination. So if you start off with ABC and you do something and you do something, you end up at 1, 2, 3. And if you go in a different direction, you also end up at 1, 2, 3. So for example, commutativity, which is if you do it in one order, you get an answer. If you do it in a different order, you get the same answer. Associativity is another example. Map, monad laws, functor laws, these are all the same kinds of things. I'm not going to get into that right now. But let me show you a concrete example. Let's say that you've got an implementation for sorting a list, and you want to check whether your implementation is correct. Now, as we said, you don't want to write a whole bunch of examples to see if your sorting implementation is correct. You want to have it want to do it for random data. So how can we do that? Well, if we take this approach, what we're going to do is we're going to manipulate the list and then sort it. That's going to be one way. And then in the other way, we're going to sort it first and then manipulate the list. And hopefully we end up at the same answer. So what we're going to do is we're going to manipulate the list by negating all the numbers in the list and then sorting it. And now, -3 should be the first answer. Now, if we do it the other way around, if we sort the list first and then we negate all the numbers and then we have to reverse the list as well, we should end up with the same sorted list, the same answer. And if this is always true, then we probably have a good implementation of sorting the list. Let's say you want to map something. So the map is a transform applied to an object or a type. And I'm going to use an example from Kent Beck's unit testing book a long time ago, where he used currency as an example. So I want to check that if I manipulate currencies, that my code is working. And again, I don't want to write some unit tests. I want to be sure that it's pretty much working for everything. So if I create a currency and then I transform it somehow, that should be the same as transforming the data before I create the currency. So let's say the transformation I'm going to do is just multiplying by 3. So if I create a currency with 2 in it, and then I map it to multiply it by 3, that should be a currency with 6 in it, hopefully. And then if I do the other way around, if I start off with 2 and I multiply by 3, and then I create that currency, I should end up at the same point. So if I don't end up at the same point, my map function is probably wrong. And so this is a nice, for things like mapping or, in LINQ, this would be called select. It's a great way to test these kinds of functions because you don't really care what the inputs are. So another common pattern for properties is doing something and then going backwards, there and back again. Let's say you want to serialize something and then you deserialize it, you should end up at the same place. If you add something and then subtract something, you should end up at the same place. If you write something and then read it, you should have the same data. They're not literal inverses, but it's basically going in one direction and then coming back in the other direction. Setting a property and then getting the property, you would expect these to work. So very, very common ways of doing testing. A classic example is doing a list. If you reverse a list and you reverse it again, you should end up with the original answer. Now, obviously, you could also just do nothing to list. So this is not the only property that you need, but it's a useful, very easy property to test. And this is a very important point. It's very rare that one individual property will do everything. You often need a combination of properties, not just one. Just like we had for addition, the individual properties, they eliminated some of them, but the combination of the 3 properties together was what really narrowed it down. So here's a really helpful property for this kind of thing, which is when you transform something, something about it is still the same. For example, the size of a collection. If you sort a collection, the size is the same. If you map over a collection, the size is the same. If you reverse a collection, the size is the same. The contents of a collection, they don't change when you sort it. They don't change when you reverse it. You often have, things like balance trees or whatever. There's some property that even if you add things to the balance trees or remove things to the balance trees, they're still balanced. That's part of the definition. Some, invariant they have. So we had this list sorting example before, and I said that was a pretty good test, but of course we haven't taken into account the enterprise developer from hell, who will try and come up with an implementation that passes this test in an evil way. Right, so this is the you can beat this test if you're evil. So the evil sort, the implementation of evil sort is literally just returning an empty list. So if you negate it and then sort it, you get an empty list. If you sort it first, you get an empty list. So no matter what you do, you get an empty list. And so these paths are the same thing. So this is one property, but there's a workaround, to make a bad implementation. So how can we improve this property so that the enterprise developer from hell cannot have an evil sort implementation? So this passes the test. Okay, so bad Garfield. Well, we can say some things never change. No matter what you do, when you sort a list, the output is going to be a permutation of the original list. It has to have the same content. And this will kill that evil sort straight away. So the sorting thing will check whether it's sorted, and then this extra property that the list has the same contents will also stop the evil implementation. So these two properties together will pretty much prove that a list is sorted. Okay, so that beats the enterprise developer from hell. And this is the kind of thing you have to do, is you have to have multiple properties. Here's another one. When you do something twice, you end up with the same answer. So if you make a distinct collection and then you make another distinct collection, it's the same as the first time. Idempotence, this is a good property. Sorting, if you sort it and then you sort it again, it's still sorted. If you do a filter and then you filter again, it's like doing it the first time. If you process an event and then you process that same event again, really nothing should happen. If you're doing any kind of distributed design, this is a really, really important property that handling events twice it's the same as handling an event once. Solving a problem, solving a smaller problem is a very common thing. If you can have a property which works for a small bit and you can extend it to the big bit, that's a nice way of doing it. And it often works when the solution is also done the same way. Like, for example, quick sorts of a list is you sort smaller lists and then you add them together to make a bigger list. So if you have those kinds of implementations, you can also have those kinds of properties. So any kind of divide and conquer algorithm will be amenable to this kind of property. Any kind of structural induction, like a recursive data structure, you can use this kind of thing for it. So very useful. Here's another one which you run into quite a lot, which is there are things which are quite hard to prove, but they're quite easy to verify. So if I have an algorithm that figures out how to get through a maze, it's hard to know, it's hard to prove that algorithm works. However, if it does give me a path, it's really easy to check whether that path goes through the maze or not. So it's often easy to check things, even though it's hard to implement them. And the classic example of this is prime number factorization. It's really easy. It's very hard to factorize numbers, but if you do have if someone gives you some factors, it's really easy to multiply them and prove that they add up to the big number. Many examples of this. I'm not even going to go into them, but this is just to show you this gives you some ideas of different kinds of things you can do. So here's an example. Let's say you have to tokenize a string using commas or any kind of parsing or tokenization. it's kind of hard to prove that the tokenizer works, especially if it's a complicated parsing thing. Here's a simple one. Let's say you just need to split something at the commas, and you get, after you split it, you get 3 different substrings. Now, testing the implementation is quite hard, but testing the output is quite easy. You just take these 3 strings and you combine them, and you should get the same string as what the input was. And so there's an example where it's easy to verify that the output is correct, even though it's quite hard to implement it. And then a more complicated thing, if you have a parser that builds up sort of complicated parse tree, it can be quite complicated to check the parser. But if you take the parse tree and you regenerate the original source code, that's a good way of checking whether your parser is working or not. Let's look at the sorting thing again. People, unfortunately, with property-based testing, people use very simple examples, and I'm not going to be an exception. The reason is it's hard to explain the stuff on a slide. So people use list sorting and list reversing and things. Real world property-based testing is much more complicated than that. And I will give you some resources for that at the end of the talk. You can check them out. Right, so let's say that we want to have something that's really easy to prove that a list is sorted. Well, it's kind of hard to prove that an entire list is sorted. However, it's really easy to check that the pairs, the adjacent pairs, are, the first one is less than the second one. So for each pair of numbers in the list, it's pretty easy to check that they're related that way. So if the individual pairs are related that way, then hopefully the list as a whole is sorted. But again, we need the property that the entire contents is the same, because again, we could have the evil sort where you just return an empty list, and that would pass too. So that's it's a quick way of verifying that something is sorted. Now the final one is something called the test oracle, and the test oracle is where you have a system under test, and you have some other system, the test oracle, that does have the right answer. And what you do is you run the system under tests, and then you run the test oracle, and you compare the answers. And if you think about it, that's really what example-based testing is too. Your brain knows what the right answer is, and you compare it with what your system says. But in real world, you often have much more complicated test oracles. For example, you have an optimized version of an algorithm, and you have the brute force version, and you know that the brute force works, but it's really slow. So you can compare the brute force version with the optimized version, and if they give the same answer for every input, then you have confidence that your optimized one is actually correct. And another example is parallel versus single thread. So you have a single thread version that works, but you want to parallelize it. Are you sure it still works? Well, just check it using, compare them side by side and see if you still get the same answer. And this is really common when you're trying to get rid of a legacy system with a replacement system, and you basically use the legacy system as an oracle for the replacement system, and you keep comparing the outputs, and if the outputs are always the same, then you have a good confidence that your replacement system is actually working the same way. Right, so let me talk about model-based testing. All these things have been property-based testing, but sometimes, and in property-based testing, we're dealing with pure functions with, they're very deterministic, they're very explicit in terms of you have this input, you always get this output. So in the real world, sometimes you have things that aren't that deterministic, like a database. Anything to do with, the real world is sometimes more complicated. And so that we can use something called model-based testing, which is the test oracle approach for sort of real world things. So let me show you how this works. Let's say that you have a simple database and you want to test whether it works or not. Okay, now a real database is incredibly complex, but we're going to test our database with just 4 operations: open the database connection, close the database connection, increment a field in a record, and decrement a field in a record. And we're going to have 2 different clients because we want to test concurrency. And what we're going to do is generate a random list of those operations. And so here we go. client A is just randomly says, okay, you open and then you increment and you close and you increment and you open and you close, and for client B, open and then decrement and open again and increment and so on. So just a random list of these 4 operations. Now, how do we actually use this to check that our database actually works? Well, what we do is we take these operations and we run it on the real system. But at the same time, we take the same operations and we test it on a very, very simple model, like an in-memory accumulator in our case. So we're just adding and subtracting 1 in the memory, So, for example, in our model, we started with 0, and then A increments it by 1, and then B decrements it by 1. Now A tries to increment it, but A has closed their database connection, so nothing happens. And then so this is our model takes into account whether the connection's open or closed, and then finally B tries to open it, tries to increment it again, and everything works. So if we do in our model, after running this, we should expect that the answer is 1. And if we run it on our real system, we should also get the answer 1. And if we don't get the answer 1, then our real world database has a concurrency bug in it. So that's a quick way of testing real world systems. And there's a great example from John Hughes, who is one of the creators of QuickCheck. They had an Erlang library, and there was this really painful bug, and they spent months trying to find out what the bug is. And John Hughes basically wrote a test to see if they could reproduce it. And he did reproduce it, and the steps were super bizarre to reproduce. You had to open and then close and then open a file, and then you had to have 3 different operations running in parallel to cause the problem. I'll actually show you. This is actually a slide from his presentation. You open a file, close a file, open a file, and the 3 different clients, one client does a lookup, another client does an insert, and the third client also does an insert at the same time. And if this happens, the database file gets corrupted. Okay. Now, what's interesting is we had these bizarre steps. No human would ever think of writing a test for this. Very, very bizarre. Why would you open and close and reopen straight away? So this was the test case. The QuickCheck found this issue pretty fast, and the shrinker is really important part of this, because you could probably find a test case where you do 20 different things in random order. But that's not very helpful to understanding what the problem is. By using a shrinker, you can actually find the minimum test case. So in this case, if you did 2 different operations in parallel, 2 clients, that wouldn't reproduce it. You had to have 3 different people doing these things at the same time. And that would be the minimal thing that would fail. So there's great John Hughes talk about this from NDC Oslo 2013. There's the link if you want it. By the way, I will put these slides on Slack, so you can look at these slides later. Right, so let's just to finish up, let's look at the difference between example-based testing and property-based testing again. In property-based tests, they're much more general. We're testing hundreds of random inputs, right? Which means that one property-based test can actually replace many example-based tests. Also, they can reveal overlooked edge cases. Like when you're doing your example test, you tend not to think about strings with non-printable characters. You tend not to think about massively negative numbers or massively positive numbers and stuff. These things should be thought about, and nulls and so on. Property-based testing, they don't care. They can just randomly generate the stuff. They're not human, And the more of a kind of deeper thought here is that understanding requirements is tricky. And property-based tests force you to think, which is obviously a bad thing. But if you do want to think, property-based tests will definitely make you think about what's important when you're testing. Now, example-based tests are still helpful. It's not either or, it's and. So example-based tests are great because they are very easy to understand. They're less abstract. They're very explicit, and 2 + 2 = 4 is a very nice little test to show me what addition does in a very simple way. So it's a great way in terms of documentation. If you really want to have a thorough testing, they're not so good for that, but they both have their place. It's not either you have to this one or the other one. You can use both example-based tests and property-based tests. So to sum up, be lazy, don't write tests, generate them, and use property-based test thinking to gain deeper insight into the requirements. So there's a bunch of resources out there on the internet. If you search for property-based testing and your language, you will almost certainly find something. All the functional languages have them. Python has a really excellent one, and I don't know about PHP and so on, but I'm sure there is one. A lot of the posts you'll see on the internet are kind of theoretical, just like my one, with very simple examples. But there are some good real-world examples out there. All the John Hughes talks are great. That's the link to that one again. He's got a couple on property-based testing. There's a really nice series of blog posts, property-based testing in a screencast editor. Like this is a real-world thing with video. How would you test that your video editor is working correctly if you're writing it? And there's an ebook there as well too. And also worth checking out is metamorphic testing by Hillel Wayne. And metamorphic testing is related to property-based testing in the sense that you change things. You don't know what the right answer is, but again, 2 different routes should give you the same answer. And the example there is, let's say you're doing image recognition. You're trying to do facial recognition in an image. Well, you don't really know where the face is, but if you rotate the source image, the facial recognition part should also be rotated. And if you make the input image black and white, that shouldn't change. That should give you the same location for the face. And if you change the colors on the input, that shouldn't change the output and so on. So you can actually do a lot of testing to check that your algorithms are correct, even without knowing what the right answer is. It's really knowing that 2 different paths give you the same answer, just like I had before. So that's worth reading. So thank you very much. That's the end of the talk. If you want to have any, I'll be on Slack after this talk to answer any questions. I will also post these links on Slack so it's easier for people to read. I have the slides and the video will be up at my website, f#fun&profit /pbt. I'm not sure if we can do Q&A at this time. I'm not sure. Can you hear me, Martin?